How about now? Okay. So I'll be talking about disentangling mergers and disks in Redshift 2 kinematic observations. This is a galaxy at a redshift of 2. This is its Hubble image. This is an average galaxy. And now we're going to zoom and look at its kinematic maps. By kinematic maps, I mean kinematics of the gas. And at any location in this map, what we see is whether the motions of the gas. So red is gas going away from you, and blue is gas going towards you. We see a rotation gradient in this system. In this galaxy, this is the velocity dispersion of the gas. So I want to highlight throughout this talk, all this work is led by my student, Raymond Simons, my former student. He's now a Giacconi Fellow at the Institute. And this work is done in collaboration with Greg Snyder, who's also at Space Telescope, and the Vela simulation team, including many of you here, Daniel Severino, Joel Primack, Avishai Deckel, Neil Menderkar. So just to kick things off, to show you how this project kind of came into play, you know, we all know kind of the classic papers like Robertson and Bullock and Huang et al. That looked at mergers and did mock observations of them and found that when you had two galaxies merging, the orbital rotation of the system, when you smeared it, and when you moved it to high redshift, which means you had to smear it, you end up seeing what looks like a velocity gradient. So what we just showed you was a major merger. This is a ground-based mock observation of it. Unfortunately, what you see here is that velocity gradient is smeared, and you can naively interpret that as a disk. I'm going to do that again, and then I'm going to show you a James Webb observation. So that's from the ground with ground-based seeing. And now this is with the near-spec IFU on James Webb. You can tell in gory detail that it is indeed a merger. We're going to now look at a different PA, a different angle around this galaxy. And again, from the ground, you're smeared, and you're duped into thinking it might be a disk. Whereas with James Webb, you can tell a lot better. You can also tell a lot better with AO. And then even with James Webb at the redshifts where Richard is looking, it's going to be hard. So one area of motivation why we started looking at this is we had done statistical studies of galaxy kinematics. And we found something called disk settling, which is essentially the increasing disk fraction with time and mass. This is one of the takeaway points on this. This is the plots. This is the observed fraction of disks versus redshift. This axis is linear and look-back time. So as you look forward with time, you see the fraction of disks are increasing. At any point in time, the most massive systems have the highest disk fractions. So we wondered, you know, could we be duped into thinking a lot of these are disks when they're actually mergers? Another reason why we want to do something, why we wanted to study this, is to determine whether whether small samples of galaxies, whether we're going after AGN, whether we're going after sub-millimeter galaxies, or even starburst galaxies, and we get IFU maps of them, can we actually tell for certain whether they're a disk or a merger? This is important to know because whether a disk or a merger tells you a lot about the physics that's going on in these systems. So locally, we can tell disks from mergers. Here we have NGC 7171 and its relevant velocity map. You see part of it's symmetric, it's nicely rotating, part of it's going away from you, part of it's going towards you. It's a disk, I think we all agree. This is the antennae galaxies, this is a local major merger. This is NGC 4038, 4039, they are merging. And in the velocity map, you pick up a tremendous amount of detail with MUSE, and then you also see the orbital rotation of the two galaxies. So locally, you can tell a disk from a merger. At high redshifts, it's difficult. This is the galaxy I started off showing you to whet your appetite. These are two more. These are from the disk sample of the high signal-to-noise disk sample from Wisniewski done with the KMOS 3D survey, which is an awesome survey of hundreds of galaxies. So you can see you have decent resolution in Hubble, but from the ground, you only have about 3 to 5 resolution elements across these systems. So what do you do when you have data that doesn't have that many resolution elements? Instead of just looking at it and making it obvious, oh yes, that is a disk, yes, that is a merger, you start creating things like criteria. I'm going to walk you through these a little quickly now, but we're going to go into them in a bit more detail. One is that the velocity gradient, the velocity map has a continuous velocity gradient along a single axis. The other one is the integrated, the total, the Vmax, or the maximum rotation velocity of the system, corrected for inclination, divided by its average velocity dispersion is greater than 1. The steepest position of the velocity gradient is coincident with the peak in the velocity dispersion profile. This is I can explain in more detail, but is essentially a characteristic of a disk galaxy. And then 4 and 5 here have to do with relating these kinematic maps to the Hubble images. Simply that the photometric and kinematic axes must be aligned to within 30 degrees, and the position of the steepest velocity gradient is consistent with the centroid of the continuum. That it's kind of going through, the velocity gradient kind of passes through the bulge. So we're going to test these criteria, and we're going to determine whether a Redshift 2 galaxy is a disk or a major merger, or at least have a shot at this, using simulations. This is what I like to use simulations for, to try to help me interpret, or one of the things I like to use simulations for, to help me interpret my observations, so whether I'm doing this right. First, we're going to establish ground truth using, or what I'm going to call the intrinsic state of the galaxy, whether it's a disk or it's a merger. We're going to do that using the angular momentum of the particles in the simulation. Then we're going to perform mock observations. We're going to create fake Hubble and IFU images like many of you have pioneered doing here, especially in Santa Cruz. And then we're going to put our observer hat on and interpret those mock observations using those disk criteria. And then finally, we're going to see how those interpretations relate to the ground truth. Are we seeing disks for disks, mergers for mergers, or is it a little more complicated? So from now on, unless I note, all the plots will be the mock observations, unless noted. So briefly, many of you are familiar with the Vela simulations, and they'll be highlighted in many of the talks here. This is just some relevant background information. These are 31 cosmological zoom-in galaxy simulations. They're done with an N-body and Eulerian galaxy gas dynamics code, the ART code by Andrei Kravtsov. They use an adaptive grid with a maximum resolution of about 17 to 35 parsecs. Star particles are of 10 to 3 to 10 to the 6 stellar masses, gas cells of 10 to the 4. So very high resolution. We're going to study galaxies in a stellar mass range that actually covers the observations at a redshift of 2. And we're going to choose galaxies at redshifts between redshifts 1 and 3 in these simulations. And we're going to post-process them using the sunrise. And the mission lines are going to be generated from the young star particles, the ones that are less than 10 million years old. Because what we observe as observers is the gas, the kinematics. So how do we identify the intrinsic state? Many of you have seen plots like this before being theorized. We're going to identify the intrinsic state of simulated galaxies by looking at the angular momentum of the particles. And specifically, we're going to look at the angular momentum of the youngest particles, less than 20 million years old, so the young stars. So I'm plotting here JZ over JCirc, which is a quantity many of you have pioneered. For each particle, JZ is the component of angular momentum that's aligned with the net rotation of the galaxy. And here we're normalizing it to JCirc. As many of you have showed, JZ over JCirc of around 1 can identify disks. Of around 0 shows a pressure-supported system. And so here are JZ over JCirc plots versus radius for all stars in gray and for young stars in blue, or showing contours in blue. Raymond actually ran segmentation maps on this, and for this galaxy was able to identify the young stars in a disk up here. So we call this a disk galaxy. For this galaxy, we have young stars in a disk and a nearby companion. We call this a disk and a companion. And then here we have no disk, or piling up around a value of 0 plus a companion. So this is how we've properly select the sample. This is JZ over JCirc of the young stars versus that of the cold gas. And it's plotted just to show you here that They're they're pretty much in decent agreement for disks, but fall apart at lower for non-disk systems. So what we end up doing is we choose disk systems as they have Jz over J squared greater than 1 over square root of 3, which roughly corresponds, using the virial theorem, to a real root of sigma greater than 1. Don't worry about exactly how we select this, because the vast majority of these I'll show you in a bit, we observe them to be disks. And then we're going to choose what we call non-disk galaxies by making a cut around a third here. And as you'll see, they are not disks. So, well, you'll see. OK, anyhow, so this is disk galaxies, and now we're going to look at some of those disk galaxies. These are mock observations of galaxies that are what we're calling intrinsically disks. This is a mock Hubble image, mock velocity map, and a mock velocity dispersion map for 3 galaxies. And you can see they all have a very nice gradient here in the rotation map, the velocity map. And in the velocity dispersion map, they have a very nice peak here. And you can see these little marks on the side show you the PAs. The PAs are pretty much in agreement with the images. These are disks. Disks are disks. We're all good for the vast majority of them. Now we're going to look at some non-disk galaxies and see what's going on with them. But first, we're going to use these, and we're going to select mergers out of these. So we're looking at so we want a clean sample when we're looking at mergers, because if we look at 2 merging disk galaxies, we're going to pick up the rotation in the disk galaxy and say, OK, that's a disk. So we're going to actually be very conservative and take 2 galaxies that are merging and only look at the ones that are non-disk galaxies. So we're going to take out the mergers, so those with a companion within a mass ratio of 1 to 30, being very conservative here. And then we're going to remove galaxies that experience a major merger in the previous time step. So there's no residuals of that. That leaves us with 15 galaxies that we do a ton of mock observations. So these are non-disk galaxies that are merging. Okay? These are 3 examples of them. These are non-disk galaxies merging. These are these velocity maps. And these are these velocity dispersion maps. Just as you saw with the antennae in one of my earlier slides, what you pick up is the orbital rotation of the motions of the system. And we were hoping that some of these criteria were able to pull them out. They're not. Let's look at the numbers on that rather than just showing you examples. So this is the fraction of sightlines. In a given in a given simulation, we have 18 sightlines all around. There are 15 of them. The fraction of sightlines where we're thinking a merger is a disk versus the angular separation of the merger. So 0, fraction of 0, we're good. We're thinking mergers are mergers. A fraction of 1, no, we're misidentifying all the mergers as disks. Using criteria 1 through 3, which rely only on the kinematic maps, you can see this fraction's all over the place. This is not ideal. And then throwing in criteria 1 through 3 are commonly used by many observers at high redshift. Throwing in criteria 4 and 5 does improve things quite a bit here, but still I'm not satisfied with this plot. So one thing we noticed is that we should add in another criterion. A lot of times you see 2 clumps in the image. And so we add in a criteria that you must have a single nucleus in the image, in the Hubble images, because you could resolve it there. And that helps think that this is criteria 1 through 5, and then criteria 1 through 5 plus adding in that single nucleus criteria. It does improve things beautifully at higher separations, but once you're closer in, you're asking yourself, gosh, is that a clump or is that a nucleus? And the segment, and because there's a lot of kind of fluff in the inner parts of galaxies, your segmentation map is not picking them up as 2. So back to the motivation, why are we doing this? We want to know whether statistical samples are affected by mergers, whether there's actually mergers hidden in here and these numbers are kind of wrong. So to do that, you need to fold in the merger rate. How common are these things? And what we did is we ended up looking at pair fractions from Illustris, from the Illustris large box simulation. They are nicely, this is done by Greg Snyder et al. In his 2017 paper. They are very nicely consistent with observations of the pair fractions. So this is the fraction of centrals, or fraction of galaxies, at redshift 2 with a pair closer than a given separation listed here for low mass and high mass. Arc seconds are at the top, kiloparsecs at the bottom. And what you notice is for kind of separations where we're looking, you can see these pair fractions are just so darn low. You're getting up to 0.07 at maximum. So we find that when running the math, we find that the disk fractions are overestimated by almost 5% at high mass. That's the red points. And almost 15% at blue mass. And that's being quite conservative. So statistically, the merger rate is just not there enough to really affect a statistical sample. But galaxy by galaxy, you have to be very careful. You need to get AO and James Webb. You cannot tell. You cannot tell whether an individual galaxy at Redshift 2 with Hubble imaging and ground-based kinematic maps is intrinsically a merger or a disk. Okay, so the conclusions are, because the pair fractions at Redshift 2 for close-in separations are so low, statistical samples are not affected by mergers passing as disks. However, we cannot tell whether an individual galaxy at Redshift 2 is a disk or a merger. So small samples are affected by this, and if you're doing a small sample, you want to go for AO, and you want to go for James Webb. And thank you very much. These are all star-forming galaxies.
Yeah, so you might be able to tell if individual galaxies are intrinsically a disk or a merger, but do you have enough information to say if an ensemble of galaxies you could recover the distribution of that such area? So you had a large enough sample.
So you need hundreds, I think, or well, you could push it, and you have a larger uncertainty on it. But you need a large sample, more like 50 to 100.
Okay. And you have enough information from the simulation to show you recover the distribution in that case? Okay, that's where I was going.
They're so, the contaminations is pretty low that you're going to recover it. We're talking 5 to, even if you assume every major merger is going to be mock observed to be a disk, you're still good.
So you talk about how often a merger is mistaken for a disk. You say it's very low because of so few mergers. But what about the other problem? How often does a disk actually get mistaken for a merger, especially in the light of the clumpiness of star formation?
There's a very nice histogram in the paper of this. I don't have it as a backup slide, but very, I think it's more like close to 90% of the time we get a disk as a disk. And there's a few cases where you have some weirdness going on, but they're really in the minority.
Even in the Vela simulation, it's only a few percent.
There's a histogram, and it's like low, 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 peak. Interpretive damage.
Okay. There we go. Are you sure?
I know it's hard to so when you're talking about the illustrious simulation and the pairs, how do you select out those pairs? Do you rely on there being 2 separately identified halos at a distance of 5 to 10 kiloparsecs?
I'm going to send you to Greg Snyder's paper because I don't know. Okay. I know he ran the light cones and did all the pair stats on this. Okay. Yeah.
So my question's more tangential. So I have this picture from your work that the set length has to do with decreasing this gas mass and maintaining a constant Q sort of naturally explains your set length. So I was wondering, looking at the simulations, are these disks that you have, sort of these marginally stable disks being star formation increasing? Is that sort of control in the simulations?
Avishai is working on this with Daniel. I think they'll be reporting back on this. But I don't, so from the observations, I don't find that. That's what you guys are finding in your simulations to match the observations. So,
Okay, I have a couple of questions. So from one thing I would put in your criteria, and maybe you tried it and it didn't work, is just the density profile. Like I would have thought that the stuff flung out in a merger would give you a density profile that was different when it's azimuthally averaged compared to non-mergers. Did you try that?
So I haven't tried that, but high redshift galaxies don't have a very nice density profile, even if they're not mergers.
Yeah.
So, I mean, a typical high redshift galaxy looks like something in the ARP atlas.
Yes. Okay. Okay. And then my other question was, I have to ask this because there's been a machine learning school going on here. So have you thought about machine learning in this context?
Yes. And I'm working with Mark Horta's company on this.
Okay.
It's hard going because we don't have a very big training sample, but
Yeah.
we're pushing it.
Yeah.
Thank
Yeah.
you.
Okay. Thanks very much.